So this is a short video on the material in section 5.3. And so this is more about what they call the fundamental theorem of calculus. There's two versions of it. And so it's more about the most important part is finding the area bounded by a curve and the x-axis. So in the last unit 5.2, we learned that, what we did is we found the area, say under like a straight, bounded by a straight line in the x-axis just by drawing rectangles and triangles. And so we're going to learn a faster way of doing doing this just by evaluating the antiderivative at the endpoints. Okay, so students, let me just jump right to the most important part here. This is the fundamental theorem of calculus right here. So I got these notes from a friend of mine who's taught the course many times. So she actually proves that prove this. So remember, what does this symbol mean right here? Do you see this symbol? I'm kind of drawing this line right here. The integral from a to b of f of x d of x. Remember, that symbol denotes, we're denoting the area bounded by the graph of f of x and the x-axis. So let's just say the curve looked like this, and here's your a, and kind of my crummy drawing here, and b. Let's say this is f of x. That this symbol right here represents the area that I have shaded in right there. And what we're saying is, if f prime of x, so find the antiderivative of f of x. And so find some function f such that f prime of x is equal to lowercase f of x. Okay, so find the antiderivative of lowercase f of x and then evaluate the antiderivative at the endpoints, f of b minus f of a, and that gives you the net area. So remember, any area, this symbol here, the integral from a to b of f of x dx, that represents the net area. So any area that's below the x-axis is actually subtracted off. So let's just look at a simple example right here. And I think I have this below right here. So let's just look at an example. Let's just look at this problem A right here. So in the last unit, 5.2, remember that integral from 2 to 5 of 2x plus 3, that represents the area bounded by the graph of 2x plus 3 and the x-axis. So from x equals 2 to x equals 5, and I tried to shade it in right there. And so in the last unit, remember what we did is that we broke that up into a rectangle and a triangle, right? We break it up into this rectangle, and then we'd find the area of the rectangle, and we'd find the area of the triangle, and then we'd evaluate them each separately. And then, there was an accurate answer. That was the area. So this one, but we can only do that for simple functions. So let's say it's not a line. Let's say it's like x to the fourth. Let's say or sine of x or something like that. It's not going to be easy to do, and we don't want to estimate with we can estimate with rectangles and draw rectangles where the width is becomes more refined, and then get a good estimate that way, and find the limit as the width goes to 0. But this is but instead we have this fundamental theorem of calculus. So the area under the curve of 2x plus 3 from 2 to 5, well, you find the antiderivative. So we know that the antiderivative of 2x is x squared, right? The derivative of x squared is 2x. And the antiderivative of 3 is 3x. The derivative, you take the derivative of this function right here, x squared plus 3x. And don't you get that? And now what we do is we just evaluate the antiderivative at the endpoint. So it's f of a. So we're going to, first we evaluate this antiderivative at 5. And then we subtract off the value of the antiderivative at 2, and we get 30. And it's just a much faster way of doing it than or I think it is. It's my own opinion. Than just taking, just kind of, drawing lots of rectangles and triangles, and it's easy to, you might, maybe there's so many steps at some point you make an error, which I know I do. I make lots of errors. Okay, so here's another one, B. So actually, I don't have a graph of this, but we know the graph of this is a parabola. So we want to know what is the area bounded by that parabola and the x-axis from -1 to 3? So remember, whenever you see these definite integrals, right? Remember, definite integral is you find the antiderivative, but it's got these, numbers here, the upper limit and lower limit. So remember, that's the area that represents the area from -1 to 3 along the x-axis. So that's the part of the x-axis we're considering, and then we want to know what is the area bounded by the curve 6x squared minus 4x plus 1 from -1 to 3. And you just take the antiderivative, right? So if you actually take the derivative of this function, 2x cubed minus 2x squared plus x, yeah, you get 6x squared minus 4x plus 1, right? Add 1, antiderivative of x squared is x cubed over 3. So 6 over 3 is 2. I think you can verify that this is the correct antiderivative. And now let's just evaluate that antiderivative at the endpoints. So it's great. So the fundamental theorem is a very important theorem. And I'm not necessarily recommending the proof of this. I don't think it's right now. I just make sure you're familiar with it. So here's one that I think would be, well, this would actually be, oh, that's my cat. I'm not sure she likes math. Okay, so anyway, okay, so let's just look at one more. So even that parabola, estimating with rectangles is not going to be necessarily that easy. But let's do that problem C there. So now, what's the area under the curve of cosine plus sine of x? And actually, I did get a graph of, it's kind of elongated graph. I got it from another website. I'm trying to fit it in. And okay, so we want to know the area bounded by the curve cosine of x plus sine of x plus from pi over 4 to pi over 2. And so here is, let's say it's about, yeah, my cat's being very difficult. Okay, so this is pi over 4. It's about 0.8. And here, this is pi over 2. And so here's this shaded in region, and we want this area right there. Okay, so again, doing the rectangles, I don't know, that yeah, that seems kind of daunting to do with rectangles. But we have this great fundamental theorem of calculus. So we take the antiderivative. What function has the derivative of cosine of x plus sine of x? Well, the derivative of sine of x is cosine of x. The derivative of minus cosine of x is sine of x. And now we just evaluate it from, and this is a pi over 4 right here. So we evaluate that function sine of x minus cosine of x at pi over 2. So we know sine of pi over 2 is 1, right? The second coordinate at pi over 2, the second coordinate on the unit circle at pi over 2 is 1. The first coordinate is 0, so we get 1 minus 0 at pi over 2. And we know that sine of x equals cosine of x at pi over 4, square root of 2 minus square root of 2. Oh, so it just turns out that area is 1. So I might think it'd be more exciting than that. Okay, anyway. But look how easy, I mean, I don't want to say it's easy. I mean, if you're finding it difficult, then I want to say it's easy. But it's really easier than rectangles. That's what I said. Let's draw rectangles and find the heights and do all the summations and keep making the rectangles, the base, just more and more refined. It'll just take us forever. Okay, so now students, so let's see. There's a second fundamental theorem of calculus, which is actually more subtle. And let's see if I can do another problem here. Yeah, here's another problem using what's called the fundamental theorem of calculus I just talked about. It's called the first fundamental theorem of calculus. And there's two of them. Okay, so now here's another one. It says, this is actually out of the homework. I think it's problem 17. Find the area of the region bounded by the graph of f of x equals sine of x. And along the x-axis, we're going from -5 pi over 6 to pi over 3. And part of the graph is below, it's above and below the x-axis. So we actually want to know, so basically, if I'm going to use the notation we've talked about before, we want to, so that area would be represented by this integral right here, -5 pi over 6, pi over 3, and sine of x dx. Okay, so remember, that's what this symbol means. So that notation there, the integral from sine of x, but when you put the upper and lower limit in, we're talking about area. Okay, so and so here's kind of a graph that I got from the Wolfram Alpha website, and so what we're looking for, first of all, remember that when you look at that notation, the integral from -5 pi over 6 to pi over 3, that's the net area, right? So it's the area above the x-axis is positive, and we subtract off the any area below the x-axis. So so the blue area would be negative and the red area would be positive, except this problem is actually not asking for the net. I'm going to do the net area later as a kind of a bonus problem. Remember, this says find the area of the region bounded by the graph of f of x equals sine of x. So it actually wants us to find the total area. So we're going to find the area. So we're going to use integrals to find the blue area and the red area, and then we're just going to add them together. And then we'll find the net area just by adding the negative part and the positive part. As a bonus, it's a bonus problem. Okay, so yeah, students other sections don't get that, just our section. Okay, so anyway, so solution, area bounded by the graph of f of x is equal to the blue area plus the red area. Okay, so let's just calculate the area bounded by in that blue area. So we're going to take the integral. So we're going to estimate that area from, let's see, right here. We're going to look at this integral right here. The integral of sine of x from -5 pi over 6 to 0 of sine of x. And we know that the antiderivative function is minus cosine of x, right? The derivative of minus cosine of x is sine of x. Yeah, remember, and then this notation, remember, represents the area. And then the fundamental theorem of calculus says, okay, well, a real easy way of getting the area is let's evaluate the antiderivative function at the endpoints. So we get minus cosine of 0, and we subtract off minus cosine of -5 pi over 6. Cosine of 0 is 1, so we get -1, and then the minus becomes plus, and cosine of -5 pi over 6 is a minus square root of 3 over 2. Yeah, we go minus square root of 3 over 2 units to the left. Okay, so so then what is the blue area? Well, we're going to have, okay, so remember, this is a negative number, right? Right, because remember when we use this integral, right? Remember that integral represents the area bounded by the function, the x-axis, but the area below the x-axis is going to be considered negative. Okay, but we want the total area, so we're going to take the absolute value of that number, and the blue area is 1 plus square root of 3 over 2. You see, that's kind of, I like those kind of numbers. Okay, anyway, who would ever think that blue area is 1 plus square root of 3 over 2? Okay, so, okay, and so then remember, how did I know to take the absolute value? Well, if x is less than 0, then the absolute value of x is I just multiplied by -1. Okay, so we just multiplied -1 minus square root of 3 times -1, and we got the magnitude. Okay, so that area under the curve is 1 plus square root of 3 over 2. Now the red area. Okay, so well, if we were in the classroom, I guess at this point I would tell everyone to put their cell phones down. Okay, but we're not. Okay, so okay, now we want the area from 0 to pi over 3. We do want the red area, so it's the integral from 0 to pi over 3. Excuse me, of sine of x dx. Once again, same antiderivative function minus cosine of x. And because of the fundamental theorem of calculus, remember, this represents the area of sine of x, bounded by sine of x and the x-axis from 0 to pi over 3. And this great fundamental theorem of calculus says, okay, well, just evaluate the endpoints. Just evaluate the antiderivative at the endpoints. So it's minus cosine at pi over 3, and then minus negative cosine at 0. So I put an extra x in here. So that, yeah, that should be cosine of 0. Okay, so yeah, so cosine of pi over 3 is 1/2. So we get -1/2 plus 1, or just 1/2. So the red area is just 1/2. No radicals or anything like that. Okay. So now we'll just add them together. The red area and the blue area is the total area. So the total area is 1 plus square root of 3 over 2 plus 1/2, or I put everything over 2. So you get 3 plus the square root of 3 over 2. Okay, now here's the bonus. This is bonus. It's not actually part of the problem. So this is a bonus problem. The net area. So the net area actually is that's what the integral gives us, this definite integral that I wrote way up here, right? This symbol right here, negative 5 pi over 6 to pi over 3 of sine of x d of x, that gives it, that's the symbol that represents the net area, meaning you add the positive area and you subtract out, the area below the curve is considered negative and the area above the curve is considered positive. So you actually might get a negative number. That looks negative to me. Looks like there's more below than above. So the net area. Okay, so we're gonna I'm gonna do it 2 ways. Okay, so let's go here. So one way to do it. Okay, we calculated the red area, and we calculated the blue area. But the blue area is the area below the curve. So the area above the curve, the red is 1/2. The area below the curve is 1 plus square root of 3 over 2. You subtract them, and you get -1 minus square root of 3 over 2. Okay, so that's one way of doing it. So now let's use the fundamental theorem of calculus. Okay, so now we'll evaluate the antiderivative at the endpoints -5 pi over 6 to pi over 3. And so the antiderivative is minus cosine of x. We evaluate it at the endpoint. So minus cosine of pi over 3. And then we subtract off minus cosine of 5 pi over 6. So a cosine of pi over 3 is 1/2. So you get -1/2. And then you get minus. So then cosine of minus 5 pi over 6 is minus square root of 3 over 2. So you get the same answer, right? It's the same answer. I guess, yeah, I could have didn't put over common denominator, but. So if you want to go directly to the net area, you would just do this. You wouldn't break it up into 2 parts. And again, the reason we broke it up into 2 parts is because we wanted the total area. Okay, so. Yeah, so we added the red area and the blue area. That's the total area. And the net area is the red area minus the blue area. Okay, so now, that was 17. Okay, so let's do problem 14. Now let's get to the second fundamental theorem of calculus, which is kind of, I have to tell you, this is my own opinion. The second fundamental, we have these 2 fundamental theorem of calculus. And the first one is really the one that you're going to use for the rest of your calculus career. And I think you see the second one in some of the problems. It's kind of a subtle, it's really very subtle. So let's look at the second, I'm going back to the notes. Let's see if I can find it. Okay, right here, second fundamental theorem of calculus. And it says, if you take the derivative, don't care about this weak form and the strong form. Okay? We're just really going to consider what's in the notes here is called the weak form. It says you take so remember the integral from x to a of f of t represents the area. That's it. So basically it's an area function, right? I don't know how I got the orange here. So we have this area function, and as x increases or x changes, we get a different area. And what it's saying is if you take the derivative of the area function is f of x. You might think, oh, well, that's kind of obvious here because like here, well, isn't the integral, let's say we take the integral from a to x of, let's say x squared, no, I'm sorry, let's put a t squared here. Well, isn't that just t cubed over 3 evaluated from x, evaluated x in an a? And then you subtract off, right? So we know that that's the antiderivative. That's what you get from the fundamental theorem of calculus. That's just x cubed over 3 minus a cubed over 3. And if we take the derivative of the, I mean, how do we get t cubed over 3? It's the antiderivative of t squared. So of course, if you take the derivative of t cubed over 3, you're going to get t squared. It seems kind of obvious. Like, what's the big deal? And it's kind of subtle. The idea is that these integrals are, the area function is an antiderivative. And there's some functions that we don't necessarily have an antiderivative we don't really have a formula for the antiderivative. And the famous one that I'm thinking of is, I think we talk about this in this course. They keep moving the, at the end, we'll talk about, about inverse functions. But here, let's see, append document. Oh, page. Okay, so the famous one, there's this function, area function, integral from 1 to x. Okay, let's say it's 1 over t dt. Now that's t to the negative 1, right? So what is it? So there, we don't actually have a formula to find the antiderivative of t to the negative 1. Because what happens, you add 1 to the exponent. Isn't that what we're supposed to do? The integral of x to the n dx, you add 1 to the exponent, and then you divide by the exponent. Well, if you add 1 to negative 1, you get 0. So how you can't divide by 0, right? So there really is no nice antiderivative. But with this second fundamental theorem of calculus, what they're saying is that the antiderivative, so let's say here's let me graph. So the graph of 1 over t looks like this. So let's start x equal to 1, or equal to, let's just start here, equal to 1. And then we got some x here. So at the second fundamental theorem of calculus is that the antiderivative of 1 over t is this area function, right? So what is the derivative? What is the antiderivative of 1 over t at some point x? Well, it says you have to actually estimate that area. And you might have heard of the natural log function. That's actually how the natural log function is defined. And it's just the natural log is really just the area under the curve from x equal 1, from a equal 1 to x. Okay, so I'm kind of gone on a long time about this. What I'm saying is that the second fundamental theorem of calculus probably will not have as many practical uses in your calculus course. It's an important theorem. If you're a math major, it's very important, but maybe not quite as important in some. You might not see it as much in your coursework, I guess is what I'm saying. I guess it took 10 minutes to say something I could say in 1 minute. Okay, but let's just look at this one problem here. This is also from the homework. Consider the following function of f and real number a. Okay, so first says find and graph the area function a of x equals, and the graph is the line. The function is the line t plus 5, and we're going to start at a equal to negative 5. So we have this function right here. I mean this integral right here. And we want to know the area bounded from a equal negative 5 to some point t. And it turns out when a is negative 5, f of t is 0. Okay, so we want to, so the area function is just the area of that green, that green triangle. And as x goes further out, the area grows. Okay, so and then you want to verify that the derivative of the area function is f of x. Okay, so so we know that, well, in this case, a is negative 5. And if here's your x, so basically the area is, I did it right here. Here's the area function, right? The width is x plus 5. The height is also x plus 5. You go out x, right? You plug x into this function right here, and you're going to get x plus 5, right? This point here is x. It doesn't look like an x to me. But that point there is x comma x plus 5, right? So this is, so we're going from a to x. A is negative 5. So the total, the base is x plus 5. The height is x plus 5. And then you just multiply it 1/2 to get the area of the triangle. So the area function is 1/2 x plus 5 squared. Okay, so the antiderivative, so the antiderivative function, not by using our rules of integration that we learned in section 5.9, but just by using the triangle, we get that the antiderivative function is x plus 5 squared. And then if you take the derivative, you just get you get x plus 5 again, right? So we did both parts here. Okay, so well, first we also had to find the graph. So you have to select the correct graph. And so it turns out, I think you can verify. Well, the y-intercept is about 25 halves, and that's the only one that looked like it had a decent y-intercept to me. Okay, and so yeah, so we found the area function just by using triangles, and we took the derivative of the area function, and we got x plus 5.